A very good afternoon, students. Today class I am going to discuss about LC oscillations. Okay. So here what is LC oscillations? Let us see that. We know that oscillation is nothing but which repeats its motion after a periodic interval of time. So what is LC oscillation? We have just got the definition that when a charged capacitor is allowed to discharge through an inductor, electric field oscillations are produced. These oscillations are called what? LC oscillation. Means when a charged capacitor is connected to an inductor, the oscillations are going to produce. Let us see how these oscillations are going to produce and what is the frequency of these oscillations in this class. Clear? Right. So I have taken a charged capacitor having charge Q and capacitance C. See, this is charged, this is positive plate and this is negative plate connected to two ends of an inductor. So now what is the energy stored in a capacitor because it is fully charged, right? Yes, energy stored in capacitor means the capacitor is fully charged. What is the energy stored in a capacitor? As we know that Q square by 2C, if charge stored is what? Q. Okay. Now what is the energy? So this is in form of which form? Electric field lines between the plates of capacitor. So this is in form of electrical energy, means electric lines of force. Okay. What about the energy stored in a inductor? Any current flowing here? No. So energy stored in an inductor. Energy stored in an inductor. UB means in the form of magnetic field lines, like 0. Now what happens? As we know the nature, it flows always from hot body to cold body, right? Hot body to cold body, high pressure to low pressure, like this. Here this is fully charged and the energy stored here is full and the energy stored in inductor is 0. Now what happens? Charged capacitor is allowed to discharge, means the capacitor starts to discharge, means the charge is flowing from capacitor to inductor. As we know, the charge is moving, the charge is varying. What happens? Charge is flowing, increasing. Discharging is what? Charge is flowing, so it is increasing. There is change of current. This change of current cause of change of magnetic flux. So change of magnetic flux induces EMF. So the current starts to flow from means the charge starts to flow from capacitor inductor, means charge is flowing, means what? Current starts to flow, means charge starts to flow from capacitor to inductor, means that is flowing in the form of what? Inductor. So the current slowly varying, it induces EMF. So this is, see here, there is no magnetic lines of force. Here because the charge starts to flow, it induces change of magnetic flux. What happens now? Slowly the charge in the capacitor decreases and the current starts to flow in an inductor. Okay. Now after some time the charge continuously flowing from capacitor to inductor. Now what is the charge on capacitor? 0. What is charge on capacitor ma? 0, means after an interval of time, after an interval of some time, what happens here? What you observed? The charge on capacitor is 0. Charge on capacitor is 0. So energy stored is 0 in capacitor. Now what about magnetic field? Energy stored in an inductor. Now what is energy stored in inductor? UB is equals to half Li square. Now the charge continuously flowed and finally the charge in the capacitor becomes empty and the current stored is maximum. Now what happens? According to Lenz's law, it opposes the induced emf, opposes change of current, right? Yes, what happens now? again the charge starts to flow from inductor to capacitor. In which direction? Opposite direction. See, here it starts from flow from positive to negative. Now here it starts from discharging. In which direction? Opposite direction. So the inductor starts to discharge and the charge flowing from inductor to capacitor. So here negative charge, here positive charge. After some interval of time, the charge capacitor starts completely charged. So what happens here? If you observe here, for every small interval from 1 to 3. So here if you take the steps here, 1, 2, 3. From first step to third step, electric field energy is completely converted into magnetic field energy. From 3 to 5, again the magnetic field energy is converted into electric field energy. Means the variation of charges has been happening here. From capacitor to inductor, inductor to capacitor, means electric field energy is converted into magnetic field energy, magnetic field energy is converted into electric field energy. So there is a variation of EMF, right? There is a variation of EMF or amplitude of energy with respect to time go on changes. So what we can say that if you consider there is generally time. If you take anything, for example, if you take a capacitor, so inductor increases and then decreases, increases and then decreases, it keep on moving like this. So this is what? Amplitude of energy. But these are not ideal. So what happens? For each and every cycle, because of heating, the current starts to flow, the amplitude of oscillation go on decreases, we get damped oscillations. This is reality, this is ideal. So we got oscillations or not, which is repeating its motion. See, 1 to 3, 3 to 5, again repeats its motion. So this cycle keep on changes and oscillate with particular frequency. Let us calculate what is the frequency it will oscillate by considering a small derivation, very small derivation. What we consider? We consider a capacitor, right? Initially, yes. Initially we consider a capacitor connected to an inductor. Let us, the capacitor is charged initially having capacitance C and charge load is Q. The inductance of the inductor is L. Now what happens here? The charge on capacitor begins to decrease, right? Initially what happens, ma? The charge on capacitor begins to decrease. Is it right? Start to decrease. We know as usual current starts to flow in the circuit. Since the charge is decreasing, we consider the current as I is equals to dq by dt, rate of flow of charge, but the charge is decreasing causing current, na? Yes, charge is decreasing giving rise to current. So we have written as what? I is equals to minus dq by dt. Okay. What is the induced EMF across the conductor? Induced EMF across the inductor, E is equals to minus L into di by dt, because it induces EMF due to change of current in the same coil. So we should consider self induction. And potential across capacitor, potential across capacitor, V is equals to Q by C. So this is a closed loop, right? Yes. What we do? Apply Kirchhoff voltage law for closed loop. For this closed loop, we apply the Kirchhoff's voltage law. What do you get, ma? V plus E is equals to 0. What is V? Q by C. What is E? Minus L into di by dt is equals to 0. What is I? Rate of flow of charge, but the charge decrease of charge rises current. So we are taking minus. So finally this equation becomes what? Minus of minus plus L into d square Q by dt square plus q by c is equals to 0. Then divide with L on both sides, d square q by dt square plus q by Lc is equals to 0. So, consider this equation number 1. So, this equation we have seen somewhere, right, in oscillations, right. So, this equation is similar to d square x by dt square plus omega square x is equals to 0, which is executing SHM. As we know, analogy, here charge, here displacement. So, what we can say that from 1 and 2 we can write as omega square is equals to 1 by Lc, that is equals to what? Omega is equals to 1 by root Lc. So, this same equation we got resonating frequency, right? Yes. So, when inductor is connected to capacitor, it oscillates with resonating frequency. So, the oscillation we got as what? Resonating oscillations. So, we said that when a charged capacitor is connected to inductor, the charge start to discharge and produce oscillations. How the oscillation has been produced, we have seen here. The variation of energy, it varies from electrical energy to magnetic energy, magnetic energy to electrical energy. Finally, it oscillates, it repeats its motion after some regular period of time. So, we are saying that it is going to produce oscillations, and the frequency of oscillations is what? 1 by root Lc. So, these oscillations are vibrating with resonating frequency. Okay. So, this is about what? Lc oscillations. And now we are going to discuss about the last concept of this chapter and the application of this chapter called transformer. Have you seen that in every street there is a transformer, right? What is the function of this transformer is, it is designed to change the voltage and current. Means it can convert high voltage to low current and high voltage low current to low voltage and high current, as well as low voltage high current to high voltage and low current. So, there are different uses to change the voltage and current. Okay. So, the main function of this transformer is what, ma? It is a device used to alternate voltage and current. So, we can change voltage or current. What is the condition? Without change in its frequency and power. Means we are not going to change its frequency and power, but we can alternate voltage and current. At last we discuss what is the special use of changing voltage. Okay, na? Yes. So, let us know what is the principle of this transformer, on which principle it works, because all the devices works on what particular principle. For example, if you take AC generator, it is a device used it works on the principle of what? Electromagnetic induction. This transformer works on the principle of, it works on the principle of mutual induction. It works on which principle, ma? Mutual induction. So, there is a rough diagram of transformer. Have you seen that? This is soft iron core and two coils are wounded on two limbs of this soft iron core. So, the two coils has specific names. This is primary coil, in which we are going to give the input, is considered as primary coil, in which we are getting the output is called as secondary coil. The number of turns in primary coil, assume that NP represents that number of turns in primary coil and NS represents that number of turns in secondary coil. So, we are going to operate alternating voltage. Okay. So, what happens? As we know, when alternating current is given to an inductor, what happens ma? It causes change in current as well as change in flux. Finally, it induces EMF. It induces EMF. What is the EMF induced here? EMF induced in the primary coil. Okay, that is E suffix P. We assume that EP is induced EMF in the primary coil is equal to what? Minus d by dt of N into phi. Actually, flux linkage primary coil is phi P. Okay. Now, an EMF is induced in the coil due to the change of current in the same coil. These are at a distance. As we know, mutual induction, what that? It induces EMF in the coil due to change of current in the primary coil or not? Yes. Then it induces EMF in secondary coil also. What is EMF induced in secondary coil? ES is equals to minus d by dt of N into phi s. We assume that for this ideal transformer, the flux linked with primary coil and secondary coil will be same. Means we are assuming one condition that there is no flux leakage. There is no flux leakage means whatever the flux that is linked with primary coil, the same flux linked with secondary coil, there is no loss of flux due to the presence of medium. So, then only what we can write? If we assume that there is no flux leakage, then I can write this as minus d by dt of N into phi. Okay. What is N here? Np, number of turns in primary coil is what? Np. Here Ns. So, minus Ns into d phi by dt. Okay. Now, this is a closed coil, but we are assuming that this is, let the resistance of the windings is 0, means whatever the resistance of the wire is there, that there is no loss of energy, then we can assume that Vp is equals to Ep as well as Vs is equals to Vs. So, replacing these values here, what are you getting ma? Vp is equals to minus Np into d phi by dt as well as Vs is equals to minus Ns into d phi by dt. These equations let divide 1 by 2. What do you get? Vp by Vs is equals to minus Np into d phi by dt by Ns into d phi by dt. Minus minus cancel, d phi by dt, d phi. What do you get? Np by Ns. So, we are assuming from first onwards what is that? For an ideal transformer means there is no loss of energy, no loss of power, means how much power we have given input, the same output we get, means input power is equals to output power. Pi is what? Input power. This is output power. What is input power? Sorry, voltage Vp into Ip. What is the output voltage? Vs into Is. This is equation number 3. From this, what you can write? Vp by Vs is equals to Is by Ip. From 3 and 4, what you can write ma? Vp by Vs is equals to Np by Ns, that is equals to Is by Ip. So, this is the relation we got. What is this relation? See here, have you observed that I have taken number of turns in primary coil 1, 2, 3, 4, but in secondary coil there are more turns, right? Yes. What happens? What happens? See, if assume that Np is greater than Ns, I am taking a condition that number of turns in primary coil is greater than number of turns in secondary coil. Then from this diagram, from this equation, what you get, ma? Vp is greater than Vs and Ip is less than Is. So what it is doing that Vp is Np is greater than number of N means what? Our input voltage is greater than output voltage. Input voltage is greater than what? Output voltage, but input current is less than output current. So this type of transformer will converts high voltage low current. See, voltage is high and low current, high voltage low current to low voltage and high current, high voltage low current to low voltage and high current. So voltage is decreasing, so that is why that transformer is called as what? Step down transformer. What it will do? It converts a high voltage low current to low voltage high current. Means what it will do, ma? It converts high voltage low current to low voltage high current. High voltage low current to low voltage high current. Simply we can write what? It is a transformer which steps down the alternating voltage, right? Because high voltage is decreased to. So simple definition of what? It is the transformer which what it will do? Steps down the alternating voltage. Okay. In a similar way, here what we consider Np is greater than Ns. Now I am taking the condition that what condition I can take here? Np is less than Ns. Np is less than Ns means what? Vp is less than Vs because these two are directly proportional and current is inversely proportional. Ip is greater than Is means low voltage high current to high voltage low current. So this function is what? Step up transformer. What the function of step up transformer? It converts low voltage high current to high voltage low current. So we can say simply as it is the transformer which steps up the alternating voltage or which converts low voltage to high voltage, right. So transformer function is what? It is used to alternate the voltage without changing its frequency and power. We have two types of transformer, one is step up and is step down. Step up condition what? Np is greater less than Ns means it converts low voltage high current to high voltage low current. Step down, it decreases the voltage means high voltage to low voltage without changing its current, power, right? Yes. Generally what is the efficiency of transformer? Efficiency of any device is output by input. So what it will give here? Output power by input power, eta is equals to output power by input power. For an ideal transformer, eta is equals to 1 means 100%. Then what we have taken? Power input is equals to power output, but it is not possible in real cases. What is power output? Vs into Is by Vp into Ip. Vs is secondary voltage, secondary current. Vp is primary voltage, this is primary current. Okay, right. Now, here we consider some ideal conditions. What are the ideal conditions we consider? There is no loss of flux leakage, right. In general, there are some energy losses. Energy losses of transformer. First one is what? Flux leakage. Flux leakage. What is the flux leakage? See, here it induces some flux, and this flux has been, the same flux has been induced in secondary coil. Is it possible in natural case? No, because whatever flux that has been induced here should flow from primary to secondary. If it is in medium, what happens? The medium absorbs some flux. So, whatever that has been produced cannot be induced in secondary coil, but we consider ideal condition, but generally there is some flux leakage. Now, to avoid this one, what we will do? We wound two coils on the same, like a mutual induction of two coaxial solids we have done now. On the same coil we are going to place insulating both coils, we are inducing. So, the gap is very less. What happens then? The flux leakage can be reduced. Next one. Resistance of windings. So, the current will flow through the coil, right? Wires. If these wires, what happens? When the current flow, it offers some resistance. That is why what we will do is, we will take the wires into small pieces and we form a bunch of wires. What happens? When you connect the wires in parallel, the resistance will be decreases. So, resistance of the windings, the loss of this energy can be resolved by connecting the wires in parallel together. Next one, eddy current loss. What is eddy currents? When a bulk conductor is placed in a changing magnetic field, it induces currents in the form of eddies. So, here a magnet is placed and the current is flowing. What happens? It induces eddy currents in the form of coils. So, causes what? Heat energy. So, that is loss of energy, right? So, that can be reduced. That can be reduced by laminating the soft iron core. If you laminate the iron core, the production of eddy currents will be decreases. So, we can reduce the eddy currents loss. Last one. This actually is not there in syllabus. Hysteresis loss. Means the magnet when undergoes a continuous variation, it loses energy. So, by selecting a soft metal, we can reduce this hysteresis loss. So, this is about complete chapter. Hope this chapter is very easy and practical point of view. Please go through the class. Any doubts we can clarify. So, by tomorrow I am going to complete the chapter by solving the problems. Thank you, students.